Okay, so let's look at the systems closely once more. Okay, so you have our system here, inputs, accumulation and production, okay, happening here. Then you have your output. So there could be zero accumulation, okay, zero production. That is also possible. So now in simpler terms, inputs, this is the symbol we use for input, MI. Okay, then our system here, which is change in mass over time, over change in time. And then we have our output, which is ML. Okay, so basically change in mass over change in time is what is accumulating in our reactors. So there'll be a change in mass over a change in time. Bear that in mind. Okay, so that is how it will look like. So change in mass over change in time is basically an accumulation of what comes in, okay? A summation rather of what is coming in or the input. So in our case of Shima, it's the summation of what? The mass of the water, okay? And the mass of the millimole minus what is leaving, isn't it? The summation of what? That Shima, which is basically water plus millimole plus production if there was any production. So in our case of cooking Shima, we found that there was no production. So P would be equal to 0 in our case. Then the mass balance for dissolved substances also equally applies, Mi minus Ml plus P. So now from our known reactions, given that we have mass is equal to Vc, M is equal to Fc, and P is equal to P is equal to RV, this equation will form this way. So this is volumetric flow multiplied by concentration. This is volume multiplied by concentration for mass flow. Okay, so we have our FIC minus FLC plus RV. This will be more clear as we begin to solve our questions. It may not make sense for you right now, but you see it later as we look at an example, how exactly we apply this one. So for each substance and water, a separate mass balance can be done. So you can have one for water and one for millimole in our case. Okay, but the equation remains the same. So this is when you're dealing with concentration. Okay, so we look at this, the meaning of terms in a mass balance equation. So what does it mean when change in mass over change in time is less than 0? Basically, when you have accumulation happening. So it means that when we have accumulation happening, it means that so meaning input and output, how do we, if we've understood the concept, how do we explain that? So if this is less than 0, if change in mass over change in time is less than 0, then it basically means that we have a negative there. Accumulation is negative. Then when this change in mass over change in time is equal to 0, then our accumulation will be negative. If change in mass over change in time is above 0, then we have a positive value for accumulation. So let's come back to accumulation and see exactly what we're talking about. Inputs, okay, what's coming in, minus what's leaving. Plus production of that substance. So let's take it, you have no production. Let's start from there. And this value is a positive value. What could be the explanation then?
Come again, madam, which value is positive?
Let's say P is equal to 0, production is equal to 0. However, this is accumulation. However, inputs is more than outputs. So in short, you put in 1 liter of water and 500 grams of millimole, but output there, the Shima was very small. What's the explanation?
Meaning there's been some materials lost in the process.
Or change in form.
Mm-hmm. So meaning something somewhere has been lost, isn't it?
Yes.
Probably remained in the pot itself, isn't it?
Yes.
Settled at the bottom, maybe. Remember when you cook shima, there's always that part that hardens at the bottom, huh?
Mm-hmm.
Okay.
Yes.
So now in that case, so meaning, so now when we come to this concept here, what does it mean? Which one is applying here? Look at accumulation on this line here. So meaning it's this one, isn't it?
Positive one.
The positive one, huh?
Yes.
Yes.
What about production? When is production negative? Remember, we have what? Accumulation and production, isn't it? So when is this P negative? What do we think?
The P is negative when the output is less than the input.
In the output. That's the one we studied at first. No, but output and input is independent. Remember, this is input and output. It's independent of P. So P entails production of that substance of the inputs. Is it multiplying in the pot, isn't it? Is there a reaction happening in your reactor that is enabling that? So if it's enabling, if there's a reaction happening in that pot of shima that is allowing for more millimole to be produced, then it means that P will be plus, isn't it? There's production happening. So now imagine a reaction where there's a chemical reaction happening that is actually taking up that millimole, okay, and breaking it down into something that is not millimole. Okay, with chemicals, it's easier to illustrate, isn't it? You have a chemical breaking down into smaller components that are not the original components. Something like that. Think of it like an organic compound, isn't it? So there's basically a reaction that is taking in or taking up the water in there and forming something else that is not water, for example. Maybe water is a bit different. Let's say let's stick to millimole, breaking it down and forming maybe into something else. So meaning it's basically sucking up, isn't it? The material. So meaning
Yes.
our inputs would be more than the output value for millimole, isn't it? Because there's something that is eating up the millimole inside the pot. That's the understanding of P being negative. I hope I've explained that. We've understood, isn't it? Then when P is equal to 0, we say that it means that there's no production, isn't it? There's no production of millimole happening in that pot. There's no production of water. There's no reaction that is happening that is bringing in more water in that pot, isn't it? So P is equal to 0. P is above 0. We've just explained that. So in terms of transport, okay, so what I mean by transport, we mean basically mass transport. Mass transport. So those input, isn't it? It moved. So you used your hands, isn't it, to put that millimole in the pot? That's transport. Then the reactions happened in the pot. You cooked, you used the cooking stick, and then you transferred that one where? To your plate, isn't it? So there's mass transfer and mass transport. Transport is more physical. It's a physical movement of the material. So those physical movement of the material, isn't it? Of the millimole on the water from wherever it came from into the pot and out into your plate. So that's why Mi minus Ml there will be above 0 there in terms of transport. So it's a positive value when you have that. Okay, so let's look at an example now of how exactly these processes, how processes happen or mass balance of an industrial process. A typical example of mass balance in an industrial process. Of course, it's much more complex than our example of Shima, isn't it? Shima is more straightforward. But in industry, it's actually not a bit, it can actually get so complicated that it's actually very difficult to keep track of each and every chemical, for example, or chemical compound, because it will keep breaking down to start reacting with other inputs and whatnot. So an example here for inputs, what can we identify as inputs? Raw materials, okay, could come in. A catalyst could be added. Water or air could be added. Power also. Anyway, power, I think someone had asked to say, could we add it as an input? Anyway, it's arguable, but it could also come in anyway as an input somehow. But the whole point of power is basically just to control the temperature. So you have those inputs there. Then what do we have as output? Gaseous emissions. You have your products that you're looking for. So your product is actually here. And you have your byproducts, including waste for recovery. Okay. Then you have wastewater coming out also. Then you have liquid waste for storage and or offsite disposal. And then you have solid waste for storage and or offsite disposal. So it gets complicated here now where you recycle. Okay, so what comes out now, you take it back inside. Okay, like with the mining industry, that's common, isn't it? What's coming out is now taken back inside the plant. And then now also here as output, you have reusable waste in another operation. So you see how complicated it gets. So so the calculations, of course, are much more complex here because you have a lot coming in and you have a lot going out. So let's try anyway. For argument's sake, let's try and track water. Let's get the mass balance for water in this case. Are we able to trace the water? So input, we have water. What's the output for water? They are able to track where water can be found on the right. Among these ones, where do you think our water has gone to?
The wastewater.
Wastewater, yes.
The product,
The product will also contain water, yes.
then the gaseous emission also.
Yes, could contain vapor.
The liquid waste. Maybe it should be basically everything on the output.
Yes, so basically almost everything on the output, isn't it? So now for you to determine the fractions from each of these outputs, you need to determine the fraction of water in them. You've seen how difficult it could be. It's not that easy, but that's what we're doing with management. It's done. It's not that it's not being done, but that's how a typical mass balance on a plant or for a process or unit operation is actually done. So everything has to be accounted for. Okay, you need to know what's going in, raw materials, and what is coming out. So all that has to be taken into account. So in terms of process control, what do you think you want to control? For example, let's look at this system. What would you think should be controlled? What do you think would be controlled in terms of process control?
More on the inputs.
Okay, so what would you be controlling?
So you can actually control the raw materials because those are going to determine the output of the product.
Okay.
As well as the catalyst. If you control the catalyst, you would know how much you would want to produce as a product as well.
Okay, so let's say someone is stealing some raw materials. Would you know from the mass balance? How would you know?
Say that again.
Supposedly someone has been stealing some raw materials. Would you know? How would you know if you would know?
You would know from how much is being produced.
So meaning you already have a value of expected, isn't it? So you already know that
Yes.
when you put in, let's say 100 kgs of raw materials, A, B, C, and D, you expect a certain kg, isn't it, of the product to be produced, isn't it?
Yes.
So basically, you've already modeled the process. So that goes in modeling, isn't it? During your design and modeling of your process. So meaning you already know expected values here, isn't it? So you're able to determine the expected volume of your product or your mass of your product. So when you don't achieve that calculated volume based on your calculated input for raw materials, then you'd know that there's something missing, eh? That would be an example. So what else would you be controlling here? Anyway, there's a number of things that you'd control, isn't it? Sometimes you may want to minimize wastewater. Okay. So maybe you determine, for example, from your process that there's too much wastewater that is being produced, okay, from this process. And you may want to reduce that amount of wastewater. So examples, maybe any examples of how you do that?
Come again?
For example, you determine that you need to control the amount of wastewater. Maybe you have too much wastewater being produced and you'd like to reduce the amount here, the volumes of wastewater. Maybe an example of how you would do it. How would you think you would go about it?
You would need to control the input of the water, first of all, as well as the discharge. The rate of discharge of the wastewater itself.
Okay. All right. Any other thoughts?
What about dealing with temperature?
Mm-hmm.
Try to control temperature so that a lot of gaseous emissions on wastewater is achieved. Then wastewater itself will be controlled.
Yes. So yes. So those are suggestions, isn't it? And there are many other things actually that you would do. So that is basically what a process engineer does. Okay. He or she would try to come up with optimum ways to reduce waste because ultimately your aim, okay, so your aim ultimately is to reduce waste on the right side on your output, isn't it? And increase this one. You want to increase the products while minimizing the rest, okay? Because the rest, at the end of the day, economically are not very important for you. So for what holds the most economic value for you is the product. So all that now goes into what we're looking at in terms of process technology. So that basically the process control, all this falls under process technology. Okay, so there's this recycle components. Okay, that is so something comes out and then it's taken back in. So now when that's now you imagine, so now you need to come up with them. So when you're coming up with the mass balance, this becomes a bit more complicated, isn't it? Because there's that loop that's been formed. Okay, so whatever has come in, will begin to react also with whatever is in here. And then now that will be a bit separate from this. So in short, all these will be disturbed because of what has come in that way. So those are some of the complexes maybe that are in reality that happen when doing mass balances. So we're going to look at 3 calculations. So there's one that involves a single component system, and there's one that involves 2 components under steady state conditions. And then the third example involves a system that includes steady and non-steady state conditions. So the same way these examples come, okay? That is how the questions also in the exam or in the test are going to be. You able to be either from these or either from these, or either one or both of any of these, in short, any combination of these, either one or 2. So there's a single component system, which is easier to understand. That's the first example we'll look at. Then there's one that involves 2 components under steady state conditions. We're going to understand a bit further what steady state means and what non-steady, obviously, which non-steady has to be the opposite of steady state condition. So let's start with the first one, a single component system. So basically you're dealing with one component. And in our example here, the problem that we're going to be solving, it is involving water, which is just one component, pure water. Okay, so it says here.
Adam, I've got a question.
Yes. Yes, please go ahead.
Just before we proceed to the examples,
Okay.
I just wanted to ask on the accumulation and the production part.
Okay.
Take for example, what you input is in a different mass, and what comes out is a different mass. Do you call that as the production, or I don't know? Okay, let's say the input is less, but the output is more. So how do you do that? Is it production, or is just output and the accumulation?
Okay, so we have to now determine the system, because there's what is known as the law of conservation of mass, isn't it? The law of conservation of mass states that whatever comes in should be the same that goes out. Okay, so mass is never lost, in short. In nature, we never lose mass, isn't it? It's just moved from one form to another. So
Yes.
now in the case where you have more inputs and less outputs, could either mean that there's production happening. Oh, sorry, there's negative production. So if output is less, isn't it? It could mean that something here. So you have 5 kg coming here, and then you have 4 kg leaving. So the 1 kg got stuck where? Here, isn't it? So meaning this is where you want to look. So it could mean that something has taken up that 1 kg. Okay, so it means that the production could be negative. There could be a reaction happening that could be using up that chemical, for example, if it's a chemical, that could be using it up in that reaction. So now in terms of accumulation, let's come to this this component here. So basically it will mean that this is more than this, isn't it? So meaning something here has to be happening here. So if there's, so it means that this should be a negative figure to counter whatever the difference here is. Okay, but in the case where the output is more, so in short, in cases where you got more shima than you expected to get from what you put in, it means that there was production of that mini meal happening in that pot. You're cooking in a small pot, but now when you put a shima, it filled the bucket. What does that mean? It basically means that something must have happened where in the pot where you're cooking from, something was multiplying the shima, or multiplying the water, or multiplying the mini meal to increase its volume, or to increase its mass. In this case, we're using mass, or to increase its mass. So it means that those production was a positive value. That's what it means.
I was basically referring that, keeping in mind that taking for example, if you are processing a mineral,
yes,
from its ore form, it could be the mass could be less than what is going to be produced. Take for example, if you're producing copper,
yes,
the copper in the ore form and what is going to come out, is more in terms of the weight or the mass. So I don't know how you could categorize that. Is it production? Is it, I don't know if it's going to balance up or something.
So you're saying, oh, so you have a certain percentage of, or a certain content in that copper ore, of pure copper, you know it.
Yes.
And then now output is that you end up having more copper than what was in the ore.
In terms of mass.
Yes, in terms of mass.
Yes.
So how, okay, I get it. Maybe there's someone who can respond before I come in. Have we gotten the scenario?
It's quite strict. Yeah, I've never encountered the copper processing, but what I think is during the processing of copper, there could be ore which is like accumulating. There's some ore accumulating, making it of more weight, to have more weight. I don't know.
Okay. Any other thoughts? Any other thoughts?
Mr. Master, can I ask Mr. Master a question?
Please go ahead.
Yes.
Eh, Is there any chemical reaction that takes place when during the processing of copper? Maybe we can start from there.
In
If
fact, there are
there's
a
any
lot of
chemical
reactions.
reaction.
There are a lot of reactions which
Okay.
occur when you're processing a mineral. Yeah, because the mineral is in ore form, it's not in a pure form.
Okay. So,
Yeah, so
probably the other
Sorry?
version I would say is maybe during the same processing with all those reaction taking place, there could be some what we can call production within processing. Yes.
Yes, so I also feel that's a quick way. Otherwise, it's not as simple as it sounds. Say you get it on ore, then you put, the copper processing line is it's huge, okay, and it consists of different reactors and different process plants, basically, for you to finally get, that mass of copper, pure copper, that is not even really pure, but 99.99% copper that you're trying to achieve. So in a nutshell, we would say that there was production of that substance. How? Because of the various chemical reactions that it's been entering into and leaving. Okay, there's been a combination of A, B, C, and there's been a lot of recycling. So what happens in copper production is this. Sorry. So what happens a lot in copper production is actually this component, this loop. Okay, this loop happens all the time. You have copper sulfates coming in, you have, so whatever, all this, so in short, in copper production, almost everything that you're counting as waste here, it's taken back into the process. Okay, so you have a lot of this moving in, okay, and then moving in sometimes combined with other soils. So it's been really, really hard for you to determine, because I would say this because, you have the same basically roots or pipes. Sometimes it will be flowing, these waters, waste waters will be flowing on just soil, okay? And, they'll be carrying with them, copper compounds, historic copper compounds, maybe from the previous month or from the previous day, and they'll flow together. So it even makes it more difficult for you to read it to the last digits to determine the mass balance in this particular case, because of the way the wastewaters run. Okay, so the movements of these things being taken back, these components being taken back into the plant process, I feel is what kind of alters in the end, which is good for production. That's the whole point why they run all these back, to try and increase, to try and maximize this one. Okay, so that could also be the other reason why. Otherwise, in a nutshell, we say that production, the fact that we'll just call it production. Otherwise, it's a bit more complex than that. I don't know if I've answered your question.
Yes, you have.
To my side, it makes sense.
Plus the other speakers, of course. I was just adding to what was said.
No, your explanation, madam, actually makes sense. I was almost asking Mr. Master to say we needed maybe to understand the whole process of copper production, because I believe a lot of us here may not have that knowledge. So for us to really respond to that, we needed just to understand the process of copper production. Yeah.
All right. Okay, so I have at least a bit of understanding from that, from KCM, because I did some consultancy there. So I go to understand the process, and it's quite complex. Anyway, from my understanding then, that is what I can conclude from my knowledge from there. Okay, so we will proceed, or maybe there are any other questions. Sorry, I didn't even invite questions. Any other questions concerning production accumulation? Okay, we move forward. We'll look at them, and there's things that are going to be with us for the next few weeks. There are terms that are going to be with us for the next few weeks. So here's a problem: a glass or a glass beaker. This is no need. Oh, by the way, there are a number of typos. Okay, in these notes. I think maybe I just need to redo them, but I'll try to make sure that we read together so that I just point out where there could be some mistakes that you may not take note of yourself. So a glass beaker with a 1 liter volume, is filled with water from a tap with a volumetric flow rate F of 0.1 liters per second. Simple calculation shows the time to fill the beaker equals 10 seconds. Okay, so V over F shows us that's equal to 10 seconds. A mass balance approach to this problem provides extra information. An equation for water level as function of time, surface area, as well as height of the beaker, surface area of the beaker, as well as the height of the beaker. So let me mention one thing. For all our calculation questions in this course, the first thing you do, whether it's a test or an exam, is draw a sketch. Because a sketch is very important to guide you to determine what kind of mass balance you need to do. If it's mass transfer, you need to help you determine what kind of mass transfer you're dealing with, whether it's mass transfer in a pipe, whether it's mass transfer on a flat plate, flow on a flat plate, or whether it's flow outside a plate. So it will help you determine. So in this case of mass balance, where we have steady for one single component system, we have steady or combination of both steady and unsteady. The sketch will help you determine whether you're dealing with steady and unsteady. So there's a set of calculations that we use for that kind of a problem. Or if you're dealing with single components, there's a set of equations that we use to find a solution to that problem and so on. So sketching is very important and it carries marks also. There's a defined designated amount of marks just for sketching. So it's very important to help you also understand the question and what is required of you. Schematic representation. So here we've been told that there's a glass beaker with 1 liter volume, isn't it? So there's a beaker of this volume and it's filled with water. So meaning the water in the beaker is what? 1 liter, isn't it? In volume, because the volume of the beaker itself is 1 liter. So if it's full, it means that it's carrying 1 liter of water. Excuse me. So it's flowing with a flow rate of 0.1 liters per second. That's the flow rate. So the definition of the system, so we define the system and set the system boundaries. That's the first step in our calculation. So here we are. Here's our beaker, our water beaker, isn't it? It's full. So the water is the red there. So that's our tap. So it was flowing at a volumetric flow rate of 0.1 liters per second. Till it got full. So it's the full height here. Okay. What else? Cross-sectional area. There we have it. So a volume. So this is the assumption is that it's a cylindrical beaker. So the volume of a cylinder is equal to H times A. So H times cross-sectional area or surface area. Okay, so we now try to get the mass balance equations for the system. Okay, so in solving these questions, the first thing you do is what? Sketch, then define system boundaries, define the system and the system boundaries. Then the next step that you do after that is to write down the mass balance equations that you're going to work with. After that, now you do the assumptions of the system. So you need to make a few assumptions before you start now calculating. So we come to the formulation of the mass balance. So change in mass over, so in this case, where is our reactor? This is our reactor. The beaker now is our reactor. Okay, this is where our system is happening. It's an open system, as you can see. Okay, so change in mass over change in time is equal to input minus output plus production. So our input mass there, which is 1 liter, is equal to So which is water, isn't it? It's the same as density. So the mass of water is equal to the density of water. We know that. Okay, so when it comes to the volumetric flow times the M there will give us density times volume. We have density times volume here. And we also have the volume, isn't it? From the geometry of our system. Our volume is equal to A times H. So we simply, in that case, we'll say density multiplied by cross-sectional area multiplied by change in height over change in time, because in this case, what is changing is the height, isn't it? So as the water was filling, what was happening to the height, basically, of the water? It was also changing, isn't it? So initially, height of water was 0, isn't it? When the beaker was empty. Then when you began to fill, the height of the water, isn't it? It formed up and it began to change over time. So there was a change in height of the water in that beaker over a change in time, which will give us this working formula. So this now becomes the working formula for a single component system. Okay, so this expression will be the same as density multiplied by volumetric flow rate. Okay, so this basically takes the position of our MI.